Okay, so this is part 3. I'm doing my machine learning homework. It helps to live stream it, gives me a bit of additional pressure, motivation, focus. So I'm trying to solve this homework exercise, which is about creating a time series neural network prediction model where I predict real GDP for a variety of countries over time. And in the last 2 videos, I did the first 2 goals, and I'm now here on the selecting the input attribute, preparing the input attributes for the neural network. And yeah, that's where I'm at. So we're going to continue from here. We're scaling, we're scaling the features for the neural network. Now, I think like what we want to do probably is some kind of simple normalization technique where I bring all of these values to some, to be like zero average, for example. So there's some time series scaling modules here in the TS-Learn library, which I'm going to use. So I think I'm going to read this a little bit and see how this works. So let's take a look at this one. Resamples the time series so that they reach their target size. I think that's not what I want. This is for clustering anyway, so I think, no, I don't think this makes sense. So let's go look at these other ones. Mean variance, min-max. Yeah, I think this might be the way to do it. Standard deviation of 1, mean of 0. This method requires dataset of equal size time series. Yeah, so I kind of have a problem that I think the time series always requires that all of the countries have the same number of years. So I'm probably going to try and take a look at that and see how we fare so far. Now, I'm not that sure how to do this. I think what I'm gonna have to do probably is like set this up to be a 3-dimensional array rather than a 2-dimensional one, because in 2 dimensions this is a bit complicated. Although, let's see. How does this group by function work? This is pandas, which I think I have open here. Wait, what's this? Oh, that's that's This applies a function while being grouped. So I think I could count the number of years per group. But the problem is it's going to... don't quite understand how this works. So, right, so we can actually get these simple things like this. We get a mean per category. So I think that's what I'm going to do just to check now how many years I have per country. So this is going to be a long list, but let's try this. Country dot count. Let's see what this does. Oops. Just replaces all of the data. It's a bit dumb. Why is that? I don't get it. Okay, no. Yeah, it just converts this thing, so it's destructive. So I'm going to need to go back and reload the data. But for now, we can see that there is quite some variance, and this is quite problematic. And what I don't see also is how continuous this data is. So this is quite problematic. I think it's probably safe to say that it's mostly fairly continuous, or contiguous, I guess is the correct way to say it. There's 118 countries on my data set, and they have let's see, they have the number of, they have oh, I see, for each column it counts how many values it has. Is that possible? But I've removed all the empty ones anyway, so it should be all identical. But in any case, okay, so the smallest one is something like Croatia with 26. And then the largest ones look like 66 years of data. So I'm going to have to get some sort of like in between where I take, I don't know, probably maybe something like 56, and then take all the ones that are more than that and delete these countries that have less than that.
It's 14:30.
Okay, thank you. Yeah, there is it's not that many that have 26. Most of them do have over 60. There's a few with 40. Maybe I even keep 66. It seems like there's enough with 66. I'm gonna reload this. Different levels of a hierarchical index. Okay, so there's animals and types. Okay, that's not really relevant for us. I mean, we could make a hierarchical index of countries and years, but I don't think we need that. We can choose to include NA in group keys or not by setting a drop NA parameter. So because column B here has NA values. Okay, it's not relevant for us. Okay, well, what really matters now is the time, like the duration of the years. So what I would need to do is drop countries that don't have all the years of all the other countries. How do I do this? So I think I might start using ChatGPT. It gives me a lot of good ideas for things like this. 3.5 can do most of these things. I think I'm going to stick with that. What's going on with my preview picture? Why can you not see the screen? Quite confused. Oh no, oh no, all my screens are frozen. I've been streaming with a frozen screen the whole time. How is that possible? I don't get it. It's still frozen. Why is the screen frozen? That's better. So something broke. Display capture. Okay, so yeah, sorry about that. I was streaming with the wrong screen showing the whole time. Okay, well, whatever. That is what it is. Okay. I only noticed that because of the dark background here, so it was very obvious. Anyway. Okay, I have a pandas data frame with panel data. Like of 118 countries dragged over 66 years. I need to clean this data for time series analysis. That means I need to select the maximum amount of data that has contiguous years for all included countries. How might I do that? Oh my god. What? Countries as rows and years as columns. No, that doesn't make any sense. Calculate the number of contiguous years for each country. This can be done by iterating over each row country and counting the number of consecutive non-null values. Okay, this seems like not a particularly smart way to do this, but okay. Find the maximum number of contiguous years among all the countries. Okay. So I wonder if I asked the same question to GPT-4 if I would get the same response. This makes more sense. So it's not assuming that I have columns for years. Yeah, in fact, he's assuming that I have the year as a column, so that's good. Start by finding the years which have data for every country. You can accomplish this by grouping the data by year, counting the number of unique countries for each year, and comparing this to the total number of unique countries in your data frame. Years that have a count equal to the total number of countries have data for all countries. Once you've identified the years with complete data, you can trim your data frame to include those years. Yep, that's cool. Check if these years are contiguous. For example, if your data contains years from 2000 to 2000, 2005, and 2007, 2010, and the years 2006 and 2011 are missing, you can identify such gaps. Yes, that's good. Okay, that's great. Thank you, GPT-4. Much better. Okay, so we're gonna just try and copy this code and see if that works. I'm gonna leave this one out. Then we're gonna run this. Just print the frame to see it works. So we have 6,400 rows as before, 13 columns. Okay, that's great. So let's see. df country and unique equals total countries. Yearly counts, df group by year, country, and unique. Full years. So I'm gonna just do these one at a time, I think. So let's do it like this. Doesn't work. Why not? Is that case sensitive, perhaps? It must be case sensitive. 118 countries, yes, as I said. Okay. And then yearly counts. Oh yeah, country and year, lowercase. Okay, length 66. So yeah, oh yeah, so it's really the early years that don't have all the countries in them. Interesting. So now I can run the full years. Which is from 1994 to 2019, which is what? That's 25 years? Yeah. 25 years. How's that? Is that enough? How many countries do I lose if I include more? I think that's better. I think I should. Oh, hold on, but how we? No, I have to think about something. So we want to predict the national GDP of each country based on other attributes. The data must be prepared in a time series. I see. So we want this model to work for all countries, but the problem is we don't have data for all countries. So if the country is an input variable, oh man, do we want the country as an input variable? I think not. I think that's too complicated because then we have to hot encode it, hot encode it, and that's a lot of countries. And that's not going to work. Even worse when I only have 25 years. Yeah, so I think we're going to make a general model and hopefully it works for all the different countries. We'll see what happens. So So we're gonna do the opposite of this basically. So yeah, it's nice. Man, GPT-4 is smart as crap. I don't actually think it's intelligent, but can summarize data much better than much better than a Google search, surprisingly. So let's see what happens if we go 66. So we want to know. We're gonna just try and run these two things. We're gonna know how many countries do we get if we exclude the ones that don't have 66 years. So it looks like a lot of countries. 46. 46 out of 118 countries. I don't think like lowering this a little bit gives us that much. We lose 5 years and then we gain. How many countries do we gain? Oh no, we gain what was it? 46. So that's 14 new countries. So 61 times 14 is. Hold on, what am I talking about? I should say 61 times 60. Oh yeah, that's much bigger than 61 times 60 is 3,600 data points. And the other one would be 66 times 46. Yeah. So yeah, this is pretty nice. So can I? What if I do a histogram of the country counts? I should be able to do this. So let me just try this. Hist country counts. I'm just gonna need. Okay, what's so the way to get the maximum amount of data is to maximize the product of the countries and years. That's crazy that this is so hard. I mean, intuitively, I'm pretty close already, I think. I don't see why this should be that computationally expensive. We only have I don't know, some several thousand points of data. Actually, isn't this like quite easy? I don't get what's hard about this. Yeah, as they say, you sort the countries by number of years, and then you go down that list. The problem, of course, is that we don't know if it's the same years, but that I think is not such a big problem. That's why I thought a histogram would help, but I don't get what's different about this than what we have. Country counts, country years. Calculate the number of years for each country. Isn't that this? Yeah. So countries by number of years. Yeah. So and then okay, how do I sort this? What is this? This is a it's actually a data frame. Actually, the year count is actually kind of better because what I can do is I can go through it year by year, right? It makes much more sense. So I'll go say, okay, I start at the back. I have 118 countries. That's perfect. So then I'm going to go backwards through this list. So I'm going to go like this: for year in yearly counts. So I'm going to do it. Why does this column not have a name? What's going on with that? Is this not a data frame? I'm confused now. Oh, it's a pandas series. Okay. it's a pandas data series. It has the year. Oh, even gives me a nice histogram here. Nice. Has the year and the number of countries with data in that year in the second column. Column? No, it's just what is a series? I don't know. I'm confused about this data structure. Whatever. You know what? I'm just gonna say looks like this. Okay, these are tuples in a series. That's what it is. Okay. Cool. That works just like that. The maximum number of data points is 4,368. Is achieved by starting from the year 1964. Huh. That is pretty dope. I guess it's let's see. So the last year has 118 countries. And then when you go back, you lose a bunch of countries at some point. What does that look like? About 100. And then, although these are bars with some width, so it could be that there's a few values in here. It goes up to 118. There might be some years where there's a little bit less as well. And so 1964 is what? How many years before? So this is what, like 25 countries that have, no, 25 years that have, oh yeah, that's what we saw, 25 years that have 118 years of data. And then you go back and you add another like 16 countries. And then you have 25 plus 16, so you have like 40 countries. And then before we did this, we added some more and we got to like 60 countries. That's probably a year, yeah. And then yeah. Okay. So, great. So the first year will be 1964. So we have data from then until 2019. Let's check that this data is now a balanced time series. My data frame is called df. Write some code to delete the years before 1964 and the countries that don't have contiguous have all the years from then until. I'll delete this. Gonna delete this. Gonna delete these ones. Okay. Copy this in. Gonna add a new block. Start removing the years before 1964. Calculate the total number of years we are considering. Get the number of unique years each country has data on. Find the countries that have data on all years. Let's do these one at a time. Okay, so yeah, so Angola doesn't work, so we're probably going to remove that country. So let's do this one. 56. Okay, good. Yeah, and then '56. Most countries have 56. Angola has 46. Armenia has 26. Okay. Oops. That's the list. Okay. Let's delete the unnecessary ones. Nice. 1964. Nice. Okay. We have 4,368 rows. That's the maximum we could achieve. This is sweet. This is really good. Yep. Man, it's pretty straightforward when you have ChatGPT. Yes, so
It's 15 hours.
So I'm gonna delete this unnecessary code here. I know that I have 118 countries. That one I need, and the rest I do not. Well, this one. Yeah. Okay. So now we have the data structured as a proper data frame for time series. Now we're going to scale the features, and now we can actually run the scaling algorithm because now we have the right structure. And this is a badly designed website. That's the regressor. Some getting started stuff. Time scalars, invariance. Yes, that's the one we want. I think that's the one we want. So the question is like whether I actually want to use this at all. Yeah, no, I think I have to because I don't think this regressor is going to handle time series data otherwise. Yeah, because in a normal if you have a specialized time series neural network, you're going to do this thing where you feed in the updates to each value over the years, and then it's kind of maps on top of each other, and we can't do that with this. So we're going to prepare this data using this time series library, and that will get it ready for the regressor. So I think this makes sense. The structure of this data is I don't know. Maybe fine. Maybe it's just this data frame maybe works. Let's just try it. So from tslearn, pre-processing, import time series scale mean variance. Okay, gonna run this, and now I can use it, and we actually don't need anything except to run the fit transform method. Fit transform does takes the data set and it does a few things. So yeah, so it does this scaling, but it also remembers it. So the oh, okay, this is maybe a problem because I want to be able to. The fit returns itself. Okay, fit to data, then transform it. Parameters, a time series data to be rescaled time series data set. Why? I do want to be able to transform without fitting though, because oh no, I'm gonna do any predictions without a transform without a fitting. So the way it works is that if you do a fit transform, normally you would do a fit transform on the input data, and then when you want to make a prediction, you just do a transformation because you want to use the same fit as you used in your training. Does this not support that? I mean, that's kind of dumb. Kind of annoyed by this. Maybe I can do the I probably have to do the pre-processing with sklearn directly. This method works on simple estimators as well as on nested objects such as a pipeline. The latter have parameters in the form of component parameters, so it's possible. So okay, so I can set the parameters, yes, but the problem is right here it says resampled time series dataset, time series to be rescaled, and here it says rescaled time series dataset. What the hell is the difference? Time series to be rescaled with the data and then transform it. I think this documentation is just not very good. I think here it's meant to say rescaled and not resampled. It's just been copied from the sampling method. Yeah, this doesn't give me a lot of trust in this whole library. So I think I'll just use the scaler that's here. What was I actually using? I think I was using a robust scaler actually, or I was using a power transformer or something like that. The nice thing about power transformer is that you can see the effects of the data much better afterwards because you get a nice distribution like this. This one is nice too. Actually don't know what is good for a neural network. What is this? Quantile transformer? Probably the power transformer makes the most sense because that is sort of how real life data works. This one is sort of problematic. If you have these outliers, you have your data mostly bunched up. That's a min-max scalar. Obviously, if you use a standard scalar with deviation and means, it's like probably a little bit better. I'm not sure if it's that much better, and this only works with the ReLU neurons, which I think we're going to use anyway, but a power transformer. Yeah. Yeah, I think I'm going to try that. Okay. Making outliers indistinguishable from inlier. I don't think that really makes sense. Robust scalar, quantile transformer. That's funny. So this has values on the bounding box. Yeah. So does this one here a little bit, but I think this is more acceptable. Yeah, I'm gonna try doing it just with sklearn. Okay, so pt equals power transformer. Okay, good. Let's try it exactly how they do it here. Yes, so when we use the power transformer, we need to remove the things that are not relevant. So let's just, for testing purposes, do this on like our output variable. Right. I think this works. That should give me a data frame for that value. Did not work though. I don't know what it's doing. Okay, let me just, I have done this before. And is it here? No, it's not here. I'm gonna have to search here in the did I not end up using it? Oh, here it is. What the hell? Oh yeah, I have this. I see. So there's a column transformer that takes the label columns and puts them, passes them through, and gives the yeah, has the other ones. So I want to recreate these two things. That is in fact this, and yes, we're gonna put that here, and it's gonna be label columns and value columns, and value columns is these ones, and label columns is just the country and the year. Okay. And then I'm gonna do all of these things. The pipeline, yeah, okay. I will, yeah, it's good if I can save it later anyway. So let's do that. Exercise 10. Okay. Pipeline is not defined. Okay, yeah, I need to import pipeline. And I need column composer, transformer. And I think that's it. See what happens. Well, it looks like it saved it. So I'm gonna close this tslearn thing. I don't like it. We're gonna just take a look at some of these things. Oops. The problem is, because it's inside the transformer, this is not going to work. I think I can just do it like this. Does that work? I do not remember. No. Sometimes stabbing in the dark here with some of these things. Anyway, I'm just gonna print my scaled thing, and then we'll see what it looks like. Yeah, I mean, it's kind of how I expected. It's got values between hovering around 0. These are all very positive. That must mean there's some that are more negative. Kind of interesting. Just these two countries, probably Argentina and Zimbabwe, are outliers on that one. Okay. Where am I on this process? Scale features. I think I've done that. So I'm just right using power transformer. Okay. I think that's fine. Let's see. Okay. Add data from the previous periods. What does that mean? Add data from the previous periods. We're going to extract. I think the point is that this is probably the point where we do the train test split. We're going to use only the periods up to a certain point, and the rest of the periods we're going to reserve for the prediction testing stage. So I'm going to get ChatGPT to help me with this. So I now have a data frame with and I'll scale it with power transformer. I now want to split off the last few years for testing purposes. Yeah, let's just do that. Yeah, I think that's fine. Okay, we're going to additionally have cross-validation, but we do want testing data kept separately. for final testing. So let's continue from here, putting the training data into a cross-validation with a hope he understands that. So my thing is called scale df. Split year is 2015. I think that's good. Yeah. Okay, that's good. So 2015 in hours, that's 2015, 16, 17, 18, 19. That's 5 years of testing data, and I have like 50 years of training data. That's pretty nice. Yeah. GPT is still writing. Okay. It's pretty familiar with sklearn, but yeah, sometimes just makes really dumb suggestions, leads you down blind rabbit holes. It's sometimes quite frustrating. So time series split I already have. Cross val score we're gonna add here, and then mean square error we're gonna add. So let's load all of these. I have the feeling it got better. I mean, this May 12th, 2 weeks ago, there was an update. Yeah, I don't think it was that good. So we've got the target variable, which is, of course, RGTPNA. Features. Well, okay. Fair enough. I actually have here at my value columns. But okay, whatever. That's fine. We find the model, hidden layers, 100, activation Rayleigh, correct. Solver atom, max iteration of 500. That seems like crazy, but okay. Time series split, n splits 5, scores. Okay, model, train features. I don't think I have numpy, so let's import numpy. Where were we? Here. So, okay, it's got this cross-val score, model, train, features, train, target. Okay, cross-validation scoring. Yes, that is what I also read before. We used the RMSE scoring, so it's good. Print square root of minus scores dot mean. What does it do when you do a negative? I mean, I don't understand that. Why would you do a negative square root? Oh my god. Don't need to ask too many questions. But okay, whatever. So there's some reason why you do that. I guess ChatGPT might even explain this at some point. Um, yes. Okay. Let's see. Model fit. Train features. Train target. Predictions. Model that predict test features. Calculate the test RMSE. Test RMSE. NP square root. Mean squared error. Test target predictions. Okay. Let's just run it. That's hold on. Root mean square error. How come it got so much better? I guess because it uses more data. Interesting. I don't know how good that is. RMSE. I guess it's pretty good. I guess it goes from 1 to RMSE. Yeah, I think that's pretty good because with the power transformation, we get values that sort of range around 0, but also typically go beyond 1 and -1. And so a sort of 11% root mean square error is yeah, that seems pretty good. Hmm. Let's see. So we've done that. We haven't done that, but we've evaluated the final model. We saved the pipeline, but we haven't saved the this model. But I think it's pretty good. So what's the
1530.
We want to optimize the hyperparameters. Now I also don't know why this was so fast because I've done the MLP regressor before and it was excruciatingly slow. What was different then? Maybe we had more data. I don't know. But this was actually surprisingly fast. So the point is that when we, so I'm gonna take this out, put it separately. So we need to optimize the we want to optimize the RMSE cross-validation, but we don't want to optimize this one because we're going to test against that at the end. So let me see what happens if I increase this to like 10 splits. So 25%. And if I make this 2, say 26, right? Okay, I think it doesn't make that much of a difference. 5 before. Okay, now I just got lucky, I think. Or was it also 23% before? I don't remember. But in any case, so gonna go back to ChatGPT. ChatGPT usually has some pretty good ideas about hyperparameter tuning, so we're gonna ask it. Okay, this is great. we are going to stay on the step for a bit, tuning the hyperparameters at the moment. My CV RMSE is 0.2372. Let's do some tests to lower it. I don't remember what the well, I don't know why I'm suggesting that, because that doesn't work with the time series database. Anyway, well, yeah, we know why it does that, because it doesn't understand what it's doing. This was not using an MLP regressor, so I was actually, as I said before at the beginning, I only ever used the MLP classifier. So, but we're gonna try and find this exercise 6. I don't think I used the regressor though, do I? Oh, I imported both. Okay. And this was to do like image to classify. Oh yeah, this was the data one that was so slow, I think. Yeah, because you have all these pixels, so you have a lot of inputs. 28 by 28. That's it's a lot. So, what was the important variables? This is what I want to know. What hyperparameters did I try and optimize on? The number of layers, or the amount of things in the layers, the alpha, the learning rate. I think the alpha and the learning rate didn't really matter as far as I remember. But okay, so this was a totally different problem, so it might not be relevant what was important here. So. Yeah, well, we know that there's limitations to using the multi-layer perceptron here, but I don't quite understand why we're just applying the randomized cross-validation. Oh, okay, because you can select that the cross-validation is the time series one. Okay, that's fine. So in that case, let's just try this. Model selection, randomized search CV. So we put that here. So I actually don't know what the syntax is. A 50 comma 100 comma 50. So this I guess would be 2 layers, 50 each, 2 layers, 100 each. Yeah, I don't know what the syntax is. Um, yeah, I really don't understand why here there's a comma and here there isn't at the end. So I don't quite understand this. Here it says array like of shape n layers minus 2. The number of layers. So if this has only one entry, then you have 3 layers, and obviously one is hidden. But if you have 2 hidden layers, yeah, okay. And then the default is the ith element is in the ith hidden layer. Yeah. Still don't get why there's a comma here. Okay, so the biggest network is the best apparently. No surprises there. H activation. Interesting. This seems to be a complicated computation. Alpha 0.1, that's the largest. Okay, I mean that's significantly better than what we've had so far. So yeah, I think let's say we don't search for that one. I think Atom is clearly going to be better. The activation. Yeah. I'm curious about how the logistic one does. If we do 2 layers like that. It seems like a lot of hidden layers when we only have like a few input layers. I wonder if it would make sense to build this up a little bit more slowly, to say like um, maybe we have 3 layers, like the outside one is like 10 on this side maybe, and 20 on this side, or 30, something like this. 21. I mean, this is much better than what we had before. So I think this logistic function does better actually than the, or maybe it's the 100 by 100. Let's see how this goes. Yeah, three hidden layers is computationally more expensive, but this is much better. So let's see if I switch now to 10H, which it found down here to be quite powerful. There is a big difference. Oh yeah, oh, what? Why is the logistic one now better when it found here that the 10H was the best one? Weird. That's a mistake. ReLU is the comparison unit here. Yeah, logistics is the best. I think it makes sense because of the power law transformed input data, and logistic puts your value to the power. So to me, like intuitively, that makes sense. I think I'm not gonna test the other ones. Maybe we just do a random search on the different layer sizes. I think I'm gonna get rid of these ones. Add one more option. Something like, let's bring this down to like 80 and then make this 20 and see if that makes a difference. What? Hold on, I'm gonna need to have these on just to have comparisons. Something like this. Okay, so it looks like the logistic is doing most of the work here, reducing this down. It looks like these two don't provide an improvement. Maybe because the alpha is not set correctly here. So let's add this. I don't know what the default alpha is. Oh, it's very low. Interesting. What does the alpha do? Strength of the L2 regularization term. That improved things, and then I turn it back into 100 by 100. It's added to the loss, so that means it's going to move faster. The model is going to converge faster, which might be a problem if you if there's lots of local optima, I believe. But in this case, it doesn't seem to be a serious problem. It definitely prefers the 0.1 to the 0.01. So let's try a few others, like a 2-layer one with 50 and 120, I don't know. And the other way around, 120 and then 50. Let's do something like that. But roughly that's the right direction to go. So yeah, I think I've pretty much done it now. So we've optimized the hyperparameters. We can evaluate the final model. We can save the final model. So the way we do that is using this. That's it. Model. That's it. All right. Oh wow, now it's been an hour and a half that I've been streaming. So that means in total I've been working on this for about 3 hours, which is not bad, I guess. I wanted to do it in an hour, but 3 hours, yeah, that's better than some of the other exercises. Yeah, so this one here, I defined 100 by 100 logistic alpha 0.1. That's what it split out from this cross-validation search. I didn't search too many things, but I think this is fair enough to show how it works. It runs for a minute, doesn't run too long. That's kind of my goal here. It goes below 0.2 on the cross-validation, which is probably just luck here, because here it's above 0.2, but I'm going to see, this is the final test, how well this does on the testing data. So let's see. This is the step 6 final evaluation of the model. 15. Yeah, not bad. It was 11 before, but that's, something you have to be careful of, that you don't like optimize to the testing data, because otherwise you're going to have overfitting to the real world data. So yeah. Just gonna add some text blocks here to say this is goals 6 and 7. Evaluate and save. Okay. This is 5. Goal 5. Create, model, and optimize. Goal 4. Split into test and train years. I think that's what's meant here. And then 3, I wrote the steps above here. So that is the power transformer is from here. So I am going to add that here. Text. Goal 3. Scale data. Okay. Good. Well, thank you for watching. I mean, I was mostly streaming for myself, but I thought I'll make this public. Maybe somebody's interested in it. Maybe somebody will learn something from it. I learned a lot this semester. This is the final exercise for this class. We've been just kind of going through these exercises, talking in class about theoretical things to do with machine learning, and then learning like this through these exercises. Yeah, I don't know if I have anything to add apart from that. If you have any questions, leave a comment. I am interested in what other people are doing with machine learning. I am a beginner, but it's something that I will be using in the future for my work, for my research. So yeah, I'm happy to work with other people, or at least help answer questions. So do reach out if you have any questions. Otherwise, see you later. Ciao.